Okay, good morning, everyone. So this will be a brief overview of the GLAMS project that was recently funded by the Italian Space Agency. It will be a partnership in between the University of Padua, CISA's center, the ICMATE section of the Italian Research Center, WASP, which is a producer of large-scale 3D printers. Now, the final goal of this project, which we hope to start soon, we haven't started yet, is to produce structural elements for lunar construction using regolith simulants, such as those that you can see in here. And we want these structural elements to have properties of macroporous materials, such as here in the central slide. In the central images, sorry, I will explain in a moment why we want them to have these properties. And we want to produce them using an additive manufacturing processes based on extrusion. So the rheological properties of these materials, the flowability, will be one of the most important properties to be assessed. So you can see on the image on your right an example of rotational rheometer by which we can assess these rheological properties. Now, shortly, the criteria that we want to meet for a lunar construction, of course, we want to minimize the amount of resources transporting from the Earth. We have to take into account all the conditions on the moon. So, for example, we have large variations in temperatures. So we want the material to be resistant to freeze cycles. So this is why we want to provide the thermal properties with this large porous network. And other conditions is low gravity, basically no atmosphere. So this can induce possible problems during the mixing of these binders. Also, the material will be exposed to micrometeoritic impact, and it has to absorb enough solar radiation. Of course, on the moon, we cannot set up real work sites, so 3D printing can be an option for the realization of these buildings. Okay, so, well, we don't want to transport, as we said, Portland cement as a binder material, not just because we want to save money and want to save fuel, but also because Portland cement in itself is a very large CO2 emitter. Okay, it is estimated that approximately 5 to 8% of the anthropogenic CO2 emissions are associated with the production of Portland cement. So we want to look for sustainable alternatives, and one of these is the production of binders by alkali activation. Okay, so we start from different kind of aluminum silicate powders, and by using alkaline solution, we can induce, as you can see on this side here, basically the polymerization of the aluminum silicate network, dissolution of the powder, and when the solution becomes supersaturated enough, we induce the formation of these reaction products called NASH because it's sodium aluminum silicate hydrate, which is the product that gives cohesive properties to the material. Okay, so this kind of alkali activated materials are also known as geopolymers. Taking a step back to from the moon to the Earth, as I said in the first presentation, it's ideally we want to give an idea of what is also the impact on the Earth that we can have with this space research. Now, to give you an idea of the amount of raw materials extracted each year, you can see from this plot, maybe the resolution is not optimal, but you can download freely this from this circular gap report 2020. So which tells us that every year, approximately 100 billion tons of raw materials are extracted. Here on the left, you can see all the different categories of materials. So approximately 40% of them are industrial minerals. On the right, you see all the different industrial sectors that are fed. And also you can see basically the construction sector incorporates approximately, again, 40% of these extracted raw materials. Okay, so you can see that of this overall stock of materials, only 10% of them are recycled. So definitely we can do better by implementing this in situ resource utilization approach also on the Earth. Okay, so this geopolymer technology can be utilized also to use different kind of industrial waste, such as fly ash that you can see here. So fly ash is a residue from coal combustion. It can also be an hazardous material. Here you can see this event occurred a few years ago in the US when some of this fly ash spilled from a containment pond and contaminated the environment. Okay, but if you collect fly ashes, it makes up a nice reactive powder made up of amorphous silico aluminate particles, and when activated using alkaline solution, it can lead to the formation of hardened material that can reach mechanical strength, compressive strength, easily up to 100 megapascal. Okay, so we have seen similar graphs before. So I said also in the previous presentation, we want to aim at those samples of our regoliths containing a larger amount of amorphous glass, which is more reactive in alkaline solution, such as those, for example, in the highland basalts. And in general, also the bulk composition of our regoliths is quite similar to those of fly ashes, although fly ash is more amorphous. So fly ash makes up a nice analog to see what we can expect by the alkaline activation of lunar regoliths. Okay, these are some preliminary study that was carried out in collaboration with the Oslo University in Norway and the European Space Agency, in which we carried out tests by alkali activation of lunar regolith simulants, and we want to test the extrudability of these materials. Okay, so what we got, we saw that the flowability of the material improved when we added small amounts of urea, and the rationale, of course, is that of obtaining the urea by extraction from the urine of the settlers of the moon bases, and also we can show that the demand of water reduced proportionally to the amount of urea added. Okay, so here you can see some results from rotational rheometry, in which again we see that the viscosity is reduced as the amount of urea is increased. And again, also on the left, we can see how the demand of water is reduced proportional to the amount of urea. Okay, this result was published in a couple of papers. And the next step is that of moving towards formed materials. Okay, so we want to improve the thermal properties of these structural units. So the idea is to implementing different kind of approach to obtain these solid foams. This is an example from a foam obtained by our partners of ICMATE. So I don't have the time to go into the details, but there are different kind of approach by which you can obtain solid foams with alkali activated materials. This is another example. You can see here an animation from 3D tomography of this foam materials obtained by addition of aluminum powders that release hydrogen in alkaline solution, so creating these bubbles. Okay, so just to conclude, so the specific objectives of this GLAMS projects is the design and optimization of the base formulation, then the optimizing of the foaming process to obtain an optimal foam stability, validating of the extrusion-based 3D printing process in the lab, realization of a scaled prototype, and finally the application of sensors to monitor the micrometeoritic impact on these elements. Okay, so just to conclude, I wanted to show up that this our studies received quite some resonance in the generalist press, where this is a couple of examples of magazines, Forbes and Wire, which cited our study. So we hope that this will happen soon, and hopefully there will be no need of implementing the training that Matthias Maurer was mentioning yesterday about broken toilets. And thanks for your attention.